So today I want to talk about functors. And functors are really, really important. So you can actually think of like all the previous lectures, they were just the introduction to functors. Okay, because functors are really what's important. I mean, mathematicians will tell you that really what's important is natural transformations, that you need functors in order to define natural transformations. Okay, and that's true, right? So, but first we have to get to functors. And why are functors so important? And I will again maybe start with a little bit of philosophy about why I personally think functors are important. Because I told you that there are things in category theory that formalize stuff that we haven't even thought was formalizable, like certain notions that are really not even mathematical. So, for instance, this whole idea of universal construction, right? I mean, what is really universal construction about? It's about being able to define what it means to be like a perfect embodiment of an idea. An ideal, right? It's like we say, how do we define a product? Well, we have all these possibilities, millions, infinity of possibilities to define a product, right? How do we pick one? And then we say, well, we'll just pick the best one. Something that's the ideal. And it turns out that if this ideal of a product exists, it's actually unique. Well, unique up to a unique isomorphism, but that's as much as uniqueness as you want in category theory. So really, something that, you know, like artists and scientists were always wondering, you know, what's an ideal thing, you know, do ideal things exist, and so on. This is just like formalizing category theory with a bunch of arrows and dots, you know. So that's, for me, this is really astonishing that you can do this, right? And we have these two types of universal construction, the one for product and the other for coproduct, and they sort of define slightly different ways of saying what is more ideal than another thing. Like, because we have all these candidates, and then we are saying, well, there is one of them that's perfect. And the property of this perfect thing is that there is a morphism coming from any other candidate, right? So that's what we use in the definition of a product, which sort of means that anything else that you throw at me can be distilled to this ideal of a product. Give me any two objects with these projections, right? Give me any object with two projections to two objects, right? And I can distill it to this perfect thing called a product, right? Because I will find a unique morphism. And this is like, you know, just finding a unique morphism, it means this is better than the other thing. And with the coproduct, we did the opposite, sort of. But it also makes a lot of sense. It means that, you know, here's this ideal coproduct, and any other candidate has in it an image of it, right? Because there is a morphism from this perfect ideal thing down to any, you know, candidate that's not perfect, right? There is this morphism that kind of embeds it, finds it inside this imperfect thing, finds this element of perfection, right? So, functors now. Functors, mathematically speaking, it's a rather simple idea. You know, you take two categories, and a functor is just mapping from one category to another, right? So why is it so important? Well, when we talked about products and co-products, right? I used a little loose language about saying, you know, we are looking for a pattern, right? So we have this pattern, which consists, for instance, of a single object that was for initial and terminal objects, right? Or an object and two morphisms that was for product and co-product, right? And now we are trying to find this pattern, match this pattern in our big category, right? And we get a lot of matches and then we find the best one, right? But, and you didn't protest, right? It's like, what is he talking about? What does it mean to find a match for a pattern, right? Because this is so obvious, right? Pattern matching is something that we do the moment we wake up until we go to sleep. And maybe even in our dreams we do pattern matching. Pattern matching is like the most important thing in understanding the world. You know, we build this image of the world, this model of the world, and we match it into reality. You know, and we try to find patterns everywhere and recognize them, right? Sometimes we find patterns where they don't exist even, because we are so tuned. It's better to recognize a pattern of a predator's eyes when there aren't any predators than to not recognize when there are, right? Because that eliminates us from evolution. So pattern recognition. So again, category theory tells us how to formalize this thing called pattern recognition. Okay? It says, okay, so if you want to recognize a pattern inside a category, well then obviously you have to define what you mean by the pattern. A pattern must be some kind of structure, right? Something, you know, like, you know, this object with two arrows, or maybe some more complex pattern, or so on. And you sort of have to map this pattern into this category. But you have to map it in such a way that you can recognize this as a pattern, which means you have to preserve the structure of this pattern, right? So what does it mean to have structure? Well, category is a definition, really, of structure. This is like structure abstracted to bare essentials. That's what category is. It's pure structure. It's just these dots and arrows, and that's structure, right? So if you want to say, I want to recognize a certain structure inside a category, it means you want to define your pattern as a category itself. You know, I mean, if it's a tiny pattern, well, it will be a tiny category. You know, I mean, you can have a category that has one object in it, right? That's a category too, and it's a pattern. Or you can have a category in which you have one object and two arrows, or three objects, right? And that's a pattern. So being able to recognize one category inside of another category is the definition of pattern recognition. And we'll come back to this when we define a more general thing called limits and co-limits, where we actually do this using these patterns. And you'll see then that actually product and co-product are just examples of limits and co-limits. But that will come later when we actually learn about natural transformations. But anyway, this is what's important: being able to define mappings between categories. So we can think of one category as being this pattern or the model, and we map it into another category, and we recognize a match for this model, or, you know, embed this model inside another category. So now that we have motivation, let's think about how we can define the mapping between categories. And obviously, to the first approximation, a category is just a bunch of objects, right? That was like the original simple-minded definition. It's a bunch of objects, right? So we have to be able to map these objects, right? And I said that these objects not necessarily form a set. It could be something bigger than a set, right? So there are these complications with being a set or being something bigger than set, and so on. But just for simplicity, just to get the idea of what we are doing, let's just consider small categories. A small category is one in which objects form a set. So if you want to map one category into another category, first thing, you have to map objects. And since objects form a set in a small category, it's just a mapping of sets. What's a mapping of sets? It's a function. So it boils down to this idea that we already studied, right? We studied functions, and we have a lot of new intuitions about functions. You know, we know the functions can do things like collapse things, right? Be non-injective by collapsing things, be non-surjective but by just covering only part of the codomain, right? So all these things that we learned about functions, they translate directly into this one part of the definition of a functor, okay? So the definition of functor contains several clauses, right? And I'll go through them one by one. But there is something funny about functions that I have not mentioned, and maybe a lot of people don't realize that functions are sort of primitive, trivial. What we really are interested in mathematics and in more general in this world is mappings that preserve structure, right? And it so happens that functions are mappings between sets, and sets have no structure. It's like, by definition, a set is this thing that has no structure, right? It just has a bunch of elements, and that's it. There is no order of these elements, right? I mean, this is why it's so hard to implement a set in programming, right? Because we are trying to map it into the hardware, and hardware is highly organized, right? And set is disorganized. It's really hard to implement something that's totally disorganized on top of hardware that's highly organized. So people implement sets as trees, really, right? But in order to implement a tree or a binary tree, right, you need to be able to compare elements, right? And so it's really, a set can be defined only when you can compare elements. That's not good. Or if you define it as a list, then there is an order in which they get into the list. So you have to think about this and say it's actually all these lists that differ only by order represent the same set, and so on. So it's really a pain in the neck. But from the point of view of mathematics, set is perfect. It says it has no structure. And since we learn about functions, we rarely think about, mappings that preserve structure. But in all the rest of mathematics, what is the most important thing is find these mappings that preserve some structure. Because we are dealing in mathematics with structured things. Things like monoids, algebras, geometrical figures, and so on. Things that have some kind of structure. So we are not really used to thinking about what does it mean to preserve structure. Okay, so we have to start thinking in terms of preserving structure. And in fact, since I said, structure is really a category, embodies structure. So since category embodies structure, is there a category that embodies the lack of structure? Like if you wanted to represent a set as a category, right? How would you do that? Yeah?
Say an object, a dot.
Well, but a set has a bunch of elements, right? A single set, right? Right?
The elements could be arrows. I think you discussed this like constant,
Uh-huh.
how to represent constants. So
Uh-huh.
you could just use the same idea.
Okay. Yeah. But arrows, unfortunately, arrows have structure because, if you say arrows, then you are saying arrows in a category, and arrows in a category,
They have to compare.
they compose, damn it, right? So there is a structure there. So, yeah, what do you think?
Category with no arrows except the identity.
Category with no arrows, right? Except identity morphisms, because we have to have identity morphisms, right? That's granted, right? But other than that, if we have no arrows, we have no structure, right? So a category is just a bunch of dots, right? With these little squigglies, the identity morphisms, right? It's a category that has a name, it's a discrete category. Discrete category is a category that has no morphisms other than the ones that have to be there, right? So a discrete category has no structure in this sense, and indeed it corresponds to a set. Well, maybe it corresponds to something bigger than a set, because a category in theory can be bigger than a set. But if it's a small category, then it's just a set. So we can represent a set as a category, right? A single set. We talked already about a category of sets in which, every object represents a set. Here we are saying, let's take one set and represent it as a category. So that can be done with a discrete category. But any category that's not discrete, by definition, has structure. So if we want to preserve structure, our mapping has to also map arrows, right? So what does it mean? Let's say we want to define a functor from some category C to another category D, right? So first of all, we define this mapping of objects. So if we have object A and object B, the functor will map this. Let's call this functor F. Let's say capital F. So this is FA, the mapping of A goes into FA, B goes into FB, right? Now in this category, we may or may not, depending on how this category is defined, we may have an arrow from A to B. Right? Let's call it F, little f. Okay? So the functor should map this F into some arrow here in this category. Well, where should it put this arrow? Right? It should map it into an arrow between some other objects, but what objects, right? I mean, obviously it must map it to an arrow between FA and FB, right? So there is an additional mapping of morphisms that has this property that if you have a morphism between A and B, then the functor maps this morphism into a morphism between FA and FB. Okay? It has to, must. Otherwise you are not defining a functor. So if you want to define a functor, you have to specify how these arrows are mapped. And notice that arrows between two objects A and B, they form a set, right? That's called the home set. And this is the home set CAB. And arrows from FA to FB form a home set in D, right? In category D, they form a home set FA, FB. But it's a set of arrows, right? So this is a set and this is a set. So a functor defines a mapping between these two sets. And what's a mapping of sets? It's a function, right? So here we have again a function. So for every home set, we have to define a function on this home set into the corresponding home set. So this is the corresponding home set for this one, right? So a functor is really a huge, potentially, number of separate functions, right? There's one big function that maps objects, and then there is one function per every home set. Okay? So that's a lot of functions. And I haven't even started talking about preserving structure, because how is structure defined in a category? Through composition, right? So, if I want to preserve structure in my category, I have to map composition, right? So let's say I have another third object, C, right, here. I'll just try to make this picture better, right? So if I have another morphism, let's say G from B to C, it will be mapped into FG here, right? So I'm mapping this morphism, I'm mapping this morphism. But now in this category, I can compose these guys and I get G after F, right? Now what is G after F mapped to? Well, it will be mapped, since it's an element from the home set from A to C, it will be mapped into an element from the home set FA to FC, right? So this will be F acting on G, F. But what about the composition of these two guys? I can compose FG after FF, right? See, I can compose these two guys. What should I get? Should I get another morphism from FA to FC? The same, right? You have to get the same morphism. That's what we call preservation of structure. Then what was multiplied here, we call this multiplication of morphisms, right? Then it has to be mapped into multiplication of morphisms here. So F of G after F has to be the same as FG after FF. Okay? So that's a condition, that's an additional condition. So I have to define these mappings on home set cleverly. Not every mapping will work. Most of them won't. Only those will work that satisfy this condition. Okay? So I have to be careful to satisfy this condition. Otherwise it won't be called a functor. It will be called something else. It will be called some kind of mapping that does not preserve structure. Okay? And the other thing, so what is category about? What is category about? It's about composition and identity, right? So obviously, if I have an idea that it has to be mapped into ID of FF, right? So ID, the mapping F of ID at A must be an identity at FA. But that's a condition that I have to impose, right? If I were just mapping these things willy-nilly, you know, the home set, like this is a home set CAA. Yeah, I'm mapping it into the home set D, FA, FA. Not every mapping is okay. I have to make sure that one particular element of CAA, namely the identity, is mapped into one particular element of this home set, namely the identity of this home set. Right? Every home set contains, every home set that is one point home set has to contain the identity. Okay? So this is the definition of a functor. A functor is this kind of mapping of objects and morphisms that preserves composition and identity. Okay? This is sort of obvious way of defining a functor. Like anything else just doesn't make sense if you want to preserve the structure. And this also formalizes this idea of what does it mean to preserve a structure, right? Because a category is structure. So functor is by definition, by this definition, is something that preserves structure. What else can we say about this functor? And this is maybe a very important thing, is that whenever objects are connected in the source category, they will always be connected in the target category, right? Because every morphism has to be mapped into a morphism. It's possible that there will be a bunch of morphisms here mapped into a single morphism here. It's fine, right? Because it's a function. It can squish things together, right? It doesn't mean that every morphism between FA and FB will have a corresponding morphism between A and B, because it doesn't have to be surjective. This mapping doesn't have to be injective, doesn't have to be surjective. We don't require that, right? So we can drop some information when we are going from one category to another through a functor, right? But we can never destroy connections. And that's very important things. So right, you know, like if you are mapping a stick figure, you know, in which you have something between the body and the head, you know, if you map it into an actual person, let's suppose that this is an actual person, right? You cannot cut off their neck, right? Because there is a connection here, there has to be a connection here. And vice versa, if you were mapping a whole person into a stick figure, right? You cannot break this connection. You can squeeze it, you know, you can, but you cannot break it. So sort of like, it reminds you, I mean, if you've done a little bit of calculus, right? It reminds you sort of continuous transformations, right? So in topology, you don't break connection, you're not supposed to break connection. So this sort of is like continuous transformation. But there is something like continuous functors, and they are more precisely defined. It's like functors that preserve limits. But essentially thinking about this continuity, you know, like what has been connected here has to be connected here. Okay? But otherwise, you can break, you can like shrink things, you can collapse things, and in particular you might define functors that don't break things, just like we defined don't shrink things, just like we defined functions that don't collapse stuff, right? We call them injections, right? So if a function is, so if the mapping of Hom sets is injective, then we call such functor faithful. Okay, so another name for this stuff, faithful. Faithful. So a faithful functor is injective on all Hom sets. Okay, and obviously there has to be another notion when it's surjective, right? So surjective, then it's called full. So a functor is full when it's surjective on Hom sets, and faithful if it's injective on Hom sets. But notice, this is why we have to have new names for these, not just injective and surjective. We have to call it faithful and full, because it's only talking about Hom sets, right? It's not talking about objects. That's very important. It's not talking about objects. So it actually, can collapse objects and still be injective on morphisms, right? Or it can map the whole category into a tiny subset of this category and still be surjective on Hom sets, right? So this is only about Hom sets. It's not, and of course the most beautiful functor is one that's fully faithful. Fully faithful functor is the one that just preserves Hom sets as they are. It's an isomorphism of Hom sets. Right? So a Hom set here maps in perfectly into the Hom set here, surjectively, injectively, isomorphically. Right? So we'll sometimes hear about fully faithful functors. So they are sort of the best possible mappings. Okay, but as far as mapping of object goes, you can go from one extreme to another extreme. You can say, okay, I'm starting with a category that has only one object, right? What's a functor whose source is just a one-object category, right? I mean, one-object category will have to have an ID, right? That's all. But this is the category we called one. The category of one object, one morphism, that's it. So if we take this category and we map it inside another category, right? We have to do the mapping of objects. So we'll pick one object, right? And what is this mapped into? Well, it has to be mapped into an identity here as well, right? Because of functoriality. Functor must map identity to identity. So once we say what object we pick here, the mapping of morphisms is automatic, nothing more. So a mapping from a singleton category, let's call it, right? Singleton category into another category is equivalent of just picking an object in that category, right? There are many such mappings because there are many objects to pick. There is another functor that picks this object, and so on. So it's just like we had with functions, functions from the terminal object, from the singleton object, right, into any other set, pick an element of a set. Same can be done in categories, no problem. The other way around is a bit interesting, right? So a functor that just maps every object in this category into one single object. Let's call it C in this category. So it collapses every single, the whole category into a single object. It's like a black hole, right? Total collapse. The whole universe collapses into one black hole. And all the morphisms here, they collapse into one identity morphism. This is an important functor. This is called the constant functor. And of course, there are many such constant functors depending on this, which objects we pick here, right? So this constant functor is called delta C, where C is the object where it collapses the stuff. That's the black hole, right? So this object totally defines the functor. Every object is mapped into this object. Every morphism is mapped into identity morphism. Period. Okay? So constant functor, very important. We'll see it. Okay, now what does all this have to do with programming? This is like the really interesting part for us programmers, right? So, first of all, most functors, well, I don't know most, but the most common functors in programming will just deal with a single category, right? Because that's the category of types and functions. That's what we have, right? But I never said that C and D have to be different categories, right? It just looks better as a picture, right? It doesn't confuse you too much, right? But in principle, it can be the same category, So objects in this category can be mapped into objects in the same category, right? And morphisms in this category can be mapped into morphisms in this category, right? And that's called an endo functor. It's like endoscopy, when they go inside your esophagus, then endo functor goes inside your category. So we can have endo functors in programming languages, right? And like in Haskell, these endo functors are just called functors because it's sort of assumed that there is only one category. So why mention even, right? So what is a functor then? Translating this, let's just take this and translate it into. So objects become types, morphisms become functions. So first of all, a functor has to be a mapping of types, okay? And it's a total mapping, right? I mean, we take this whole category, and every object in this category has to have an image there, right? So it's a total mapping of types, which means it's a type constructor. In Haskell, we call it type constructor. In other languages, you might call it a parameterized data type, right? Or a template type, or something. Generic type, right? We have all these names for like a whole family of types that is parameterized by other types. Okay. But that's just one part of a functor, right? The type constructor is the mapping of types. So that's this one function that works on objects. But it also has to map morphisms, which means it has to map functions, right? So it has to be defined for functions. Okay, so let's just grab some examples and see how we can define, starting with a type constructor, how can we define the mapping on functions? So, our friend, maybe, right? And in other languages, it's called option or optional, right? Depending on the language. Data, maybe, of A. So A is the parameter, it's the type that we are parameterizing of. A can be integer, can be Boolean, can be whatever, right? So for every type A, we are defining a new type called maybe A. Okay? So we are mapping types to types. So A, the functor maybe, maps A into maybe A. That's our mapping of types. Right? So if this is an integer, this is maybe of integer. Boolean, maybe of Boolean, and so on. Right? So we have a mapping of types. Now this is defined as, in Haskell, as nothing or just A. That's the definition, right? It's a coproduct of unit and identity, right? So, is this a functor? Well, what would it mean for this to be a functor? It would mean that we have to define some kind of mapping of functions between home sets, right? So if we have A and we have some B, right? B will go into maybe B. We have to define now a function that will go from maybe A to maybe B. So if this is F, this is the mapping of F using the functor, okay? Now this mapping of functions, at least in Haskell, is called fmap. It has like the same name for all functors. Fmap of F, okay? And so fmap of F is a mapping between maybe A and maybe B. And that corresponds to what we are defining here, right? So let's see what I can erase here. I can erase this. We might need this stuff. Okay. So let's just see. Oh, so fmap is a function that takes a function from A to B. So a function from A to B has the type A arrow B and produces another function that goes from maybe A to maybe B. Okay? So this is the type signature of fmap for the maybe functor. Okay? So like if in Haskell we don't have to specify which fmap we mean, but in mathematics maybe we would say fmap maybe. Okay? Because fmap is defined differently for every functor. In Haskell we just give it a name fmap for every functor, and we'll see in a moment how we can do this so that we have this kind of polymorphism, right? But fmap for maybe must be of this signature, and let's try to define it. Okay? Let's try to implement it. So how do we implement fmap, a function that takes, okay, so fmap takes some function f, so that's the function from A to B, that's this guy, and produces a function that goes from maybe A to maybe B. So let's give it a maybe A and produce a maybe B. right? So, and maybe A can be either nothing or just. So we have to consider two cases, right? So let's consider nothing case. And separately, the second case will be f of just some x. Right? We have to define these two cases. And it's trivial, really, right? Right? I mean, so what is this? It has to be a maybe of B, maybe B.
Nothing.
Nothing. Can we put anything else here?
On top.
Here, yeah, instead of nothing. Could we put something else here?
Bottom.
Bottom. Okay, let's not talk about bottoms. Okay. Yeah, that's always in Haskell, because it's a lazy language. It's always possible to put a bottom here. But let's pretend we are in ML. Huh? No bottom. So and they have some optional type. So is there anything else we can put here? Any ideas? Are we really forced to put nothing here? Is that because our imagination is bad, or yeah?
I mean, we could be silly and just put just f of x just to screw things up.
Just what?
Oh.
Just
oh,
what?
We don't have anything. That's right. We don't have anything.
Just what? Yeah. Damn it, because we don't have an A, we don't have a B,
We just
right?
have nothing.
Yes?
Could you do stupid weird stuff with absurd and recursion?
That would be more like if infinite recursion, that would give us a bottom, right? Non-infinite
Oh, yeah.
recursion would give us some type which is not maybe B, right? So that we have a mental block as programmers here, right? We cannot imagine anything else but nothing, right? But the truth is we could say okay, well, let's say it's nothing unless the type A is integer. Or
Just 0 or something like that.
just 0.
Just 10. Just.
Yeah, if B is an integer, just 0. Right? Why not?
It's a maybe.
What's wrong with that? Is there something wrong with that?
It's silly.
Yeah?
Iron breaks polymorphism? Because you have to
Well, but what's polymorphism? Yeah?
We have to do it for all A's.
Well, so I said for all A's, just like for all A's, it's nothing except for one, right? Now, you are on the right track in the sense that we want to use polymorphic functions in a language, and the language, Haskell, kind of tells us that the function should be parametrically polymorphic. Okay? So if we say we are in system F, which is parametrically polymorphic, right? That we have only certain ways of constructing polymorphic functions using a single formula, then this is the only answer. Okay? But there is something called ad hoc polymorphism, right? There is parametric polymorphism, which will prevent us from doing anything else. But there is also something called ad hoc polymorphism. And ad hoc polymorphism is one which we say, well, for everything except for integer, do this, and for integer, do something else. And it's a perfectly legitimate kind of polymorphism, except that we don't want to use it here, right? But it's really important to understand that we are kind of, when we are doing programming, even in programming in Haskell, we are straying from mathematics a bit, right? we are actually imposing a stronger condition than being a functor. We are imposing this condition of parametric polymorphism. Once we impose this condition that it has to be parametrically polymorphic, we are making it much more restrictive. Okay? And it's so restricted that it actually leads to this so-called theorems for free. Right? I don't know if you guys heard something, this people talk about the theorems for free and so on. So this is something that says, because in Haskell we actually can only implement polymorphic functions of some limited kind, right, that are a certain type of polymorphism, right, then that imposes additional conditions on what we can do. Okay? But it's important to remember this, right? But for a moment, let's forget about it. So indeed, this is like the only choice. Right? For parametric polymorphism, this is the only choice. Now, for this guy, we have a little bit more choices. Even if it's parametrically polymorphic, we could say this is nothing, right? We could say it's nothing. And it's still polymorphic. Now, probably, I don't know, maybe this is a homework, like, figure out, if we put nothing here, will this actually be a good functor or no? Yeah, will composition work? Will functor laws work? I don't know. So I'm just like teasing you, right? I don't want to talk about this, but the obvious choice is of course say, yeah, just, and let's act with F on this X, because X is of type A, F turns A into B, so let's act with F on this X and reconstruct a just, right? And this is a typical way of implementing functors, you know, just a functor usually has something of type A in it, right? A functor on A will have something of type A inside, and you can just apply this function to the insides of the functors. And in a moment I'll talk about this and in a little bit more detail. Okay? So, is this a functor? So we define the mapping of types. That's the mapping of types, right? Or objects. Let's say objects. Object mapping. And this is morphism. Morphism. There is still something missing, right? I mean, that's full definition of mapping, but we still don't know whether this is a functor, right? We don't know. Is it mapping identity into identity? Kinda obvious that it does, right? And does it preserve composition? That's a little bit less trivial. So maybe we should take a break now and come back to this question later. Okay?